Okay, it's 3 o'clock. Monika, are you ready?
Okay, I'm also muted. No, I'm not. Yeah, I'm ready.
Okay, great. Our last talk in the contributed sessions for the afternoon will be Monika Kudlinska from Oxford, speaking about quasi-isometries of free-by-cyclic groups.
All right, thank you very much. Thank you for the opportunity to talk. So today I'm going to be telling you a little bit about quasi-isometries of free-by-cyclic groups. And if my, great. So motivation obviously comes from the world of geometry. I mean, this is a geometry topology workshop, so it better be. So a three-manifold is said to fiber over the circle if it's the total space of a fiber bundle where the base space is a circle, obviously, and here the fiber is necessarily a surface. So examples of such three manifolds, triple knot complement, figure eight knot complement, bunch of knots. More generally, every hyperbolic three manifold fibers if you allow yourself to pass the finite covers. So this is the content of the virtual fibering conjecture. Now, if you have a three manifold that fibers like this, there's this long exact sequence in homotopy, which in this case reduces to this short exact sequence on the level of fundamental groups. And in particular, here you have the group on the right-hand side is just a free group, it's just the infinite cyclic group. And so this short exact sequence splits. And so your fundamental group is a surface bicyclic group, we call it. So it's a semi-direct product with the normal factors surface group. Okay, and this leads me to my next definition. So let f of n be a free group of rank n. My free groups will always have finite rank. A group then is said to be free bicyclic if it's isomorphic to this semi-direct product of a free group by an infinite cyclic group. So as per the previous slide, we can see that whenever I have a three manifold which fibers over the circle and the fiber is an orientable surface with non-empty boundary, then the fundamental group admits this nice splitting as a free bicyclic group, since here the fundamental group of a surface with boundary is just free. Now, if that was all, then this would be a very boring talk. But free bicyclic groups are actually much more general than just three manifolds which fiber. So here, suppose gamma is I forgot to mention it should be a finite graph. And I take a homotopy equivalence of this graph phi, then I have this mapping torus construction, which is essentially just taking the graph, crossing it with the unit interval, and then identifying the bottom and the top layer via this homotopy equivalence. And this is called a mapping torus. So the fundamental group of such a space is free bicyclic. Such a space is also aspherical. This is essentially how we can construct geometrically these free bicyclic groups. So again, you could ask, well, maybe actually secretly here I am just talking about three manifolds again. So the answer is definitely not. One way to see this is whenever I have a homeomorphism of a surface and I look at the growth. So I look at how if I iterate the same homeomorphism on some curve, or on a collection of curves, and I look how the length of these curves grows, then in the case of surface homeomorphisms, so mapping classes, when the growth is polynomial, it's actually almost linear. So I can never realize growth, polynomial growth of degree higher than 1. Whereas in the case of homotopy equivalences of graphs, you really can get polynomial growth of any degree that you fancy. And so that's one way of seeing that these guys are not all three manifolds. And there are other more subtle ways to see that as well. So generically speaking, a free bicyclic group is not a fundamental group of a three manifold. But it's a good thing to think about if you keep in your mind as an example if you haven't seen these groups before. Okay, so on to the next term in my title, quasi-isometries. So if you haven't seen this before, let xy be two metric spaces. A map between these metric spaces is called a QI embedding, a quasi-isometric embedding, if essentially it's coarsely by Lipschitz. So for any 2 points in the domain, the distance between their images in the codomain is controlled by the distances in the domain in this uniform fashion. So such a map is a quasi-isometry if, in addition, it's coarsely dense. So for every point in the codomain, I can find a point in the domain that maps uniform bounded distance away from that point. Okay, so why are we talking about these funny maps? Well, suppose you have groups, you have a finitely generated group, you want to study it using geometry. Okay, you want to put a metric on it maybe. There's a very natural way to do this via this construction called the word metric. So you take some finite generating set S of your group, and you put a norm on your group on the elements where you say the length of an element is the smallest number of generators and their inverses required to express that group element as a word in these generators. And this actually gives you a norm on your group, and you can use this norm to define a metric on the group. And we call this the word metric with respect to this finite generating set. Now, there's an issue with this, right? I made a choice. So I chose my finite generating set. In general, there are many different generating sets that I could have selected. And we would like to say that it didn't matter which finite generating set I chose. So unfortunately it does, but only up to quasi-isometry. So essentially, if I choose 2 finite generating sets of my group, then the identity map of my group is a quasi-isometry with respect to these 2 different generating sets, 2 different word metrics with respect to 2 different generating sets. So there's a slight ambiguity there. And then, of course, there are other ways that you might want to assign a metric to your group. For example, if your group is already associated to a space that has some geometric structure, like a manifold, for instance. So suppose G is the fundamental group of some manifold that I'm here asking for it to be compact. Then, of course, the group acts by deck transformations on the universal cover of this Riemannian manifold. And I can look at the, I can look at the orbit map. So I can just choose some element, some base point downstairs, lift it upstairs, and then see how these elements, how far they move this base point from itself. And it turns out that this orbit map is actually also a quasi-isometry if I fix any word metric on G. So, and here detailed as just the pullback of the Riemannian metric to the universal cover, and M tilde is the universal cover. Okay, so you see, so there are many different ways to put a metric on a group, and they're all defined up to quasi-isometry. And so the motivating and very natural question to ask, how much of the algebra of my group is preserved under quasi-isometry? So how much information are we losing each time we pick a different geometric model? How much can the situation change? Okay, so I just need to introduce one more concept, and that's virtual isomorphism. So suppose I have 2 finitely generated groups. They are said to be virtually isomorphic if I can find finite index subgroups, hi in GI, and then finite normal subgroups of these finite index subgroups, such that when I mod out, the results are isomorphic groups. So sort of the slogan is that they're isomorphic up to a finite amount, up to finite error. And we call this virtual isomorphism. Now, the reason why I'm introducing this is because whenever 2 groups are virtually isomorphic, they are in fact quasi-isometric. So this is in essence like the best we can do. So we're always going to be have to be satisfied with losing that a little bit of information, by passing to finite index subgroups or quotienting out by finite things. But this is usually not so bad if we're working with infinite groups. And so that's just what we have to live with. But of course, the main question is, when can this implication be reversed? So when is this like the worst possible thing that can happen? And this really has motivated like geometric group theory research for the past 20 years, 30 years, ever since Gromov first talked about this concept. And so this motivates my next definition. So a group is said to be QI rigid, quasi-isometrically rigid, if whenever there's another group H, which is quasi-isometric to my group G, actually H is forced to be virtually isomorphic to G. Okay, so this is the reverse of that implication that we had on the previous slide. Now, sometimes we want to make a slightly more general definition, and that is for a class of groups to be QI rigid, which just means that whenever I have a group H, which is quasi-isometric to some element in this class, this group is virtually isomorphic to possibly another element in this class. Okay, this is what it means for the class of groups to be QI rigid. Okay, some examples. So finite rank free groups are QI rigid as a class. Whenever I have something that's quasi-isometric to some finite rank free group, it actually has to be virtually isomorphic to it. But free groups themselves are not QI rigid. So if I take, say, free group of rank 3 and a free group of rank 4, these two guys are quasi-isometric to each other. So, you know, even free groups themselves are not QI rigid. And sort of closer to where I'm getting, and closer to the topic of this conference, the class of closed hyperbolic three-manifold groups is also QI rigid. But you know, as we saw above, they are all quasi-isometric to the three-dimensional hyperbolic space with the hyperbolic metric. So they are themselves, they are not QI rigid because they're not all virtually isomorphic to each other. Okay, and you could have probably guessed the question that I'm interested in is whether the class of free-by-cyclic groups is QI rigid. And this is still an open problem. Why do we think this might be true? Well, there isn't really a good reason. It's more, we sort of, a lot of results in free-by-cyclic groups happen to be true for three-manifold groups, and then by some miracle also were true for free-by-cyclic groups. So we're hoping that this will extend to this problem as well. But yeah, there's no really good reason to think that free-by-cyclic groups are QI rigid, apart from the theorem on the next slide, which is sort of towards answering this question. So this is a new theorem. I'm going to just read it out and then define all the terms in the theorem. It's a bit of a mouthful. So suppose I have a group G, and this group has finite cohomological dimension, and it virtually has this property of being residually finite, rationally solvable, or RFRS for short. Then if G is quasi-isometric to a free-by-cyclic group, it's actually virtually a free-by-cyclic group. So I probably should have mentioned this before. When I say something's virtually something else, it means I can take a finite index subgroup that satisfies this property. Okay, so this theorem basically is saying that the class of free-by-cyclic groups is QI rigid in the bigger class of groups of finite cohomological dimension, which are virtually RFRS. Okay, so it's not really answering the question from my previous slide, but it's giving some evidence towards this question being true, at least for these groups. Okay, so let's unpack this definition, this statement. First of all, cohomological dimension. If you haven't seen it before, a group has cohomological dimension n over the integers. You can define this over other rings as well. If for every degree d greater than n and any zg module m, the cohomology of G in this degree D with coefficients in M vanishes. Okay, so this is maybe a little much to take in, but you can think of this, so any group with a finite classifying space, so any, say, fundamental group of a spherical manifold of any dimension, sorry, will have finite cohomological dimension. So non-examples are finite groups, but of course, quasi-isometries don't distinguish between finite groups. So all finite groups are quasi-isometric to the trivial group. So it's sort of this geometric way of studying groups kind of falls apart if you care about finite groups. But yeah, thankfully we're talking about infinite groups. Okay, so this is cohomological dimension. It's not such a restrictive condition. So in fact, if I have two groups, both of which have finite cohomological dimension, if they are quasi-isometric, these groups, then the cohomological dimension is equal. So here in particular, my G will have the same cohomological dimension as any free-by-cyclic group, and all of these groups have cohomological dimension 2. Okay, so all these groups will have cohomological dimension 2. And I guess another nice fact to know is that groups of cohomological dimension 1 are exactly free groups. Yeah. Okay, slightly more seriously is this refers condition. So it's technical, so I'm not going to give the full definition, but very roughly, a group is said to be refers if every finite subset of G can be separated in the abelianization of some finite index subgroup. So this condition was cooked up by Ian Agel. He was studying when he was trying to prove the virtual fibering conjecture. So Danny Wise then showed that hyperbolic three manifolds are virtually special, and so refers and sort of more generally, virtually refers groups include all subgroups of right-angled Dalton groups, all rags, and so all virtually special groups. So this is a fairly large family of groups. There's quite a lot of groups to play with there. Okay, so for the last couple of minutes, I'm just going to give you a couple of, a brief sketch of what goes into the proof of such a statement. So again, I'm not going to be giving any definitions in this next slide, so it might just not make any sense to most of you, but it's just in case someone's interested, you can either ask me or Google. Okay, so sketch of proof. So first of all, we need a way of characterizing when a group admits a map to Z with finely generated kernel. So we actually use the word fibering for this as well. So just remember, like we had the three manifold fibered over the circle. Here we have a group that fibers. That just means it admits a non-trivial map to Z with finely generated kernel. So if a group fibers, then actually all of its L2 Betti numbers vanish. So here L2 Betti numbers, they are in some sense, well, they are dimensions of some homology groups of G, but actually there's a little more going on. So these are von Neumann dimensions of Hilbert modules. But anyway, L2 invariants are a very powerful tool for answering all kinds of different questions, and they prove to be very useful here as well. So if a group fibers, then its L2 Betti numbers vanish. And vanishing of L2 Betti numbers is a QI invariant. So the property of all the L2 Betti numbers vanishing is an invariant of quasi-isometry. If one group satisfies this property and you have another group that's quasi-isometric to that group, then that group also satisfies this property. So always QI invariants, you look for them in order to prove some QI rigidity type results. Okay, so now we have this QI invariant. And finally, the last piece of the puzzle is a result of Sam Fisher, who will actually, I'm advertising his talk. He will talk here on Wednesday, in fact, about this result. And he showed that any group that has this homological finiteness property of being of type FP K over Q. Okay, again, I'm not going to say what this means, but any group with this property, if its reefers and the first K of its L2 Betti numbers vanish, then G fibers. So then G admits a map onto Z with kernel of type FPK over Q, in particular finally generated. And so you put all of these pieces together, you then apply a couple of fairly standard results from homological algebra, and you get this QI invariance type result. Okay, thank you very much.
Okay, let's all thank Monika.
Hello, can I ask a question?
Yes, of course.
So could you go to the slide where there was quasi-isometry mentioned for H3? Yes. So which group is in the second bullet? Is it all isometries of H3 or?
This is all the fundamental groups of hyperbolic three manifolds, closed hyperbolic three manifolds.
What does it say? But they all are quasi-isometric to what exactly?
No, that any group that is quasi-isometric to some closed hyperbolic three manifold group is actually virtually a closed hyperbolic three manifold group.
And what is this H3 for?
And this, sorry, what do you mean?
Like there is reference to a group seems to be missing. If I read, but they are all quasi-isometric to just H3.
Oh, sorry, yeah. Yeah. Just a hyperbolic three space. Yeah. With the hyperbolic metric.
About groups being quasi-isometric or
well, so quasi-isometry I've actually defined for spaces, for metric spaces.
So
I can I just realized
any three manifold is quasi-isometric to H3. Does it say that?
Yes.
Okay.
Yes.
Thank you.
Yes.
Thank you.
By Schwartz-Milner. Yeah.
Okay. Thank you.
Yeah.
Any other questions? All right, if not, let's thank Monika again. And we'll all meet back here in about 40 minutes for the, a little less than 40 minutes for the first talk by Jessica Purcell. And that will be in this room. And if anybody wants to hang around and chat, feel free.